graduated from the University of Otago in New Zealand in 2015. I last gave a talk to you guys on this research, I think right before I started as a PhD student. So in the last 5 years, since almost 6 now, since I got my PhD, I've been doing research on early baleen whales and dolphins from the Oligocene epoch of South Carolina. Right after the baleen whale dolphin split, about 25 to 30 million years ago. Those are a lot of the fossils we have here. I am still working on a fair bit of research on fossils from my own neck of the woods, much closer to you guys on the other side of the bay, up in Santa Cruz, and in this photograph, HALFMOON Bay. So let's talk local fossils. No longer for me, but for you guys. Marine mammal fossils from Santa Cruz and HALFMOON Bay, dramatic faunal change over the past 4 million years on the Pacific coast. All right, most of you guys have a biological background, so some remedial geology is required here. Geology is pretty strange to think about, and most people don't think about what's happening under their feet. So there's 3 major types of rock: igneous rocks, which are, granite and basalt. Those are rocks that form from either magma or lava. Metamorphic rocks are rocks that have been subjected to heat and pressure and sort of cooked or smashed. And then there's sedimentary rocks. Sedimentary rocks are rocks that form thin layers of sediment, and those are the ones that have fossils in them. Examples of different sedimentary rocks include sandstone, mudstone, shale, diatomite, and limestones. Another thing you're going to hear a lot, the word formation. A rock formation is not like, the way my mom would use the word would be like the goblin little erosional features in Bryce Canyon, Utah, or like the big buttes at Monument Valley. A rock formation is actually a mappable body of rock, usually going to be sort of a thick layer, and it can be anywhere from a few meters to several kilometers thick, and mapped out over an area maybe the size of the Bay Area, or like the entire continental western US. There are some rock units that extend from Canada to Mexico and from California out to Colorado. So we've got a geologic map of Santa Cruz. It's tilted a little bit. There's a couple of rock units here that are important. The yellow unit is the Santa Margarita sandstone that is about 10 to 12 million years old. And that's where people go and they dig for shark teeth in the Santa Cruz Mountains, right around Scotts Valley. The dark brown unit along the coast makes up all those incredible cliffs between Año Nuevo and Davenport and like Bonnie Doon State Beach. That's the Santa Cruz mudstone, which is about 7 to 9 million years. And I'll give you guys a time context here in a minute. The pale green color, that's the Parissima Formation. And it also extends out to the cliffs between Steamers Lane and Aptos, only it's covered by that gray unit, which is an Ice Age deposit. If we look in the subsurface, we see this. Ben Lomond Mountain is all the way on the left, and that is this basement bedrock, which is Cretaceous granite. And that is overlain by all of these different post-Cretaceous, rocks deposited after the extinction of the dinosaurs. All these marine layers. So the Parissima you can see is that unit that's the pale green, and then it's overlain by Pleistocene terrestrial deposits called the Aromas red sands. So that's what the cross-section of this area looks like. The southern Santa Cruz Mountains and the Santa Cruz coastline are very important fossil sites, and I'll explain why shortly. Now, time-wise, the geological time scale is broken up into all these different periods and epochs and geological eras. So there's the Paleozoic era, which is the age of fish, Mesozoic era, which is the age of reptiles. It's when dinosaurs, the very first mammals and birds, all evolved. They all go, dinosaurs, aside from birds, go extinct 66 million years ago, leading to the Cenozoic era, which is often glossed over in a lot of books on fossils and paleontology because, oh, the age of mammals is boring or something. But it's the one that is closest to us in time. It's the one we need to study the most if we want to understand modern ecosystems. The Cenozoic is divided into a bunch of different epochs, which generally range from about 10 to 15-ish million years or so. Some are as short as 2 million years, like the Pleistocene. And I'll cover the Eocene through Pleistocene history of whales here in a minute. All these time periods are based upon the fossils that were found in those rock layers. And then we had these dates. You can see all the way on the right-hand side, 66, 56, 33.9, et cetera. Those are radiometric dates made using radioactive isotopes like uranium lead series dating, potassium argon dating, et cetera. Like radiocarbon dating, but much longer half-lives for different isotopes. We're going to be focusing on these two time periods, the Pliocene and Miocene epochs, and roughly the period between 7 and 3 million years ago, which is what is represented by the Parissima Formation. Okay, now here we've got a family tree of all cetaceans, and not all of them, but there's at least a couple different members for each family present. So if we look down here, we've got Zygorrhiza and Georgocetus. Those are two early Archaeocete whales. Georgocetus still has hind legs and it can still walk around on land. It's from the Middle Eocene. By the late Eocene, we had the first fully marine whales like Zygorrhiza. Sometime in the late Eocene or earliest Oligocene is when the Mysticetes separated from the Odontocetes. So we've got baleen whales and the toothed whales. And these are two different major clades within Cetacea. And there's the Odontocetes. The modern sperm whale is the most primitive, so to speak, of all the toothed whales. And the group is generally defined as the common ancestor of Physeter and a pilot whale. But then there's all these other extinct groups, which are the ones I'm studying right now. Most of the fossils I'm going to talk about belong to modern or recently extinct families of cetaceans. Now, time-wise, the ancestral whales, the Archaeocetes, evolved from land mammals during the early Eocene, roughly 50 to 55 million years ago. During the Oligocene, we get the very first echolocating whales, which is a synonym of toothed whales, because we think they were echolocating extremely early, and the very first baleen whales. A lot of the earliest baleen whales still had teeth, so some of these are very strange-looking cetaceans. During the Miocene, we get the first members of modern groups, and most modern families, for example, the Delphinidae, oceanic dolphins, these families show up during the middle and late Miocene. Sperm whales show up right at the beginning of the Miocene, for example. During the Pliocene, which is roughly 5 to 2.5 million years, it's a very short epoch, we get the earliest occurrence of extant genera. So, for example, the oldest records of bottlenose dolphins, Perseops, show up during the Pliocene, though they're just a little bit different from the extant species. The earliest records of Balænoptera, minke whale-like whales, I'm going to talk about one of the earliest in this talk, show up during the Pliocene. When we get to the Pleistocene, we get mostly extant species. There are some Pliocene holdovers, but most extant species don't show up until the Pleistocene. The Pleistocene is basically the Ice Age. And the Ice Age is really about 15 or so glacial interglacial switches, where you'll have like a 20 to 30,000 year interglacial period separated by or followed by a glacial period and then back to interglacial, and it oscillates. We'll talk a little bit more about that later on. Now, some of you guys may have seen Jurassic Park almost 30 years ago, and they show this beautiful carnivorous dinosaur skeleton being excavated. And that's often not how we find them, or how they look at all when we dig them up. Sometimes it is. So this is a beautiful baleen whale from the late Miocene of Chile, found about 10 years ago. Most of the time when I find fossils, they look like this. So this is from Opal Cliffs in Santa Cruz. And that's a single lumbar vertebra of a small dolphin or porpoise, that little brown thing. And a little bit of it's been eroded away. This is a boulder that fell off of the cliff and then slowly eroded through by the waves. All those little white things are shells. I go around every time I see something like this, every bone bit that looks potentially interesting, I just collect a chunk of rock around it. I don't care about identifying in the field because the tide's coming in and you don't have a whole lot of time. And I'll talk more about that in a moment. Oftentimes you end up with a lot of broken bits of ribs and vertebrae that don't tell you very much. But 1 out of 10 of those bone chunks can be something interesting. And sometimes you'll find something that's pretty obviously not just a bone fragment when you find it in the field. Why do marine mammal bones so frequently preserve as isolated elements? Part of the problem is that marine mammals live in the ocean and they're pretty fatty, and often have a lot of guts. And on top of that are also housed in this really thick blubbery skin. So oftentimes you have this initial stage called bloat and float, where decay gases build up in the gut cavity. Because of all that blubber, it's kind of hard for small to medium-sized predators, or scavengers, I should say in this case, to rupture that body wall. So often the carcass will float around for a long time, and it'll start shedding some of the bones that are at the extremities, the jaws, the skull, bits of the flipper bone, so on and so forth. And then eventually, after losing a bunch of these, some of these bones will fall to the seafloor, and then the remainder of the carcass will end up sinking as well. So you often have these really incomplete skeletons where it'll be like a string of vertebrae, a femur, a humerus, scapulae, etc., maybe some ribs, but nothing anatomically informative like a skull or a mandible. And often the teeth all fall out. And then the bones can also be colonized by invertebrates. I'm sure some of you guys are familiar with the concept of a whale fall. Whale falls aren't really present in the Perissima Formation because the Perissima Formation represents water depth that's too shallow. But if you go back in time into deeper marine rocks, you find fossil whale falls, which is pretty neat. All right, further complicating these, the discovery of marine mammal fossils in the Perissima Formation is the fact that most of the exposures are coastal. So you got to plan everything around high and low tide. Digging or just looking for fossils in the summer is pretty bad because the lack of waves allows all sorts of dust and salt to build up on the cliffs, and it kind of obscures the fossils that are normally poking out. So storms will erode away at the cliff, but also clean it off. This site in particular, somewhere in Half Moon Bay, erosion there is so slow, it's best to check it once a year. Unlike the Badlands in Montana and the Dakotas, you don't have this really extensive outcrop. All your outcrops are just two-dimensional vertical cliffs. So you're really limited. In Santa Cruz, I can more or less cover every single known outcrop that's likely to produce a lot of vertebrate material in about 2 or 3 days. Timing it, of course, with the tide. You can't do an 8-hour day in Santa Cruz. Just there's not enough low tide for that. Because you're near urban centers and some of these fossil sites are well known, you also end up competing with amateur collectors. If you're smart like I am, you end up making friends with these amateurs and you identify fossils for them, and occasionally they'll give you one. If you tell them it's really important, you can also invite them to come out and help on digs. They love that sort of thing. There's also some localities that are only accessible by boat, and I think I've got one on the next slide. This excavation shows one of the problems with excavating fossils from cliffs. In this case, it was probably about a 200-pound plaster jacket. We take burlap, dip it in wet plaster Paris, and harden it, and it protects the fossil from being damaged during transport back to the museum. In this case, it was about 7 or 8 feet above the beach, and if we just rolled it down the cliff, it would have broken apart pretty easily. So we dug it out over a couple of days, then built this sand ramp. Used a bunch of driftwood to sort of, allow it to be steeper than normal, and sort of a pseudo-Egyptian way of dealing with it. This is at Drake's Estero in Marin County. I got a permit through National Park Service to do some field work here about 10 years ago or so. And that's me with paleontologist Dick Hilton at Sierra College in Rockland. And we paddled on a canoe about 3 miles back and forth every day to this spot. And right here, this is the mouth of the Estero. And so on some occasions, it would actually get pretty choppy and wavy. And we've got a 200-pound block with a complete walrus skull inside. And I was worried that if the canoe tipped, that walrus skull would go straight to the bottom of the Estero forever. There was no way to really secure it into the canoe. It was so heavy that we wouldn't really be able to flip the canoe back over if it was secured. So we crossed our fingers and it got back, and it's a beautiful skull, but that was pretty nerve-wracking. Oh yeah, and there it is sitting on the cargo net we used to move it. Here's some other examples of challenging field locations. On the upper right, that's another spot at Point Reyes. Right about the level of Dick Hilton's knees in that photo is the high tide line. We had about 2 hours between when this photo was taken and when the water would get up to that spot. It rises really quickly there, much faster than I'm used to in Santa Cruz. And that a lot of that's probably got to do with the fact that we're on an estuary. Unfortunately, that day I found 3 or 4 large fossils below the level of his feet. So I dug like a maniac to get those out. On the lower right, that's the same whale in the bottom of the cliff. And then my buddy Chris Perrone, who's an amateur collector who lives in Foster City, near my parents actually, we found this baleen whale skeleton about a foot down from the top of that cliff. I collected an ear bone from it, which is now at Berkeley, but there's no way we can safely collect the rest of that. So I'm more than happy to let that erode away. That's like a 40-foot cliff there with a drop straight into boulders and waves. Now, when you do get fossils, sometimes there's small bits that you can sort of just scrape off with a dental pick. Occasionally, you get concretions. And by occasionally, I mean a lot. A lot of skulls are preserved in concretions, which are basically zones of sandstone or siltstone that are hardened with calcium carbonate, which is the mineral that marine invertebrates make their shells out of, and the same mineral that makes up limestone. So this is basically a limestone nodule within the sandstone. On the left-hand side, we've got a dwarf baleen whale brain case that's about 2 feet wide. I found that at Capitola in 2009 or so, and I brought it back to Montana, where when I was a master's student, I started preparing it with a little bit of acid just to weaken the rock, and then with mechanical pneumatic tools, so little things called air scribes, which are little mini jackhammers. That is slow going, and it will give you carpal tunnel and possibly some bad neurological problems called white finger, where it kills a bunch of nerves from all the vibration. It takes about 10 hours or so to remove about 1 kilogram of rock. And that thing weighed about 70 or 80 pounds. I couldn't walk for about 3 days after I lugged that off the beach. But I got it done, and it's a beautiful skull, and I really need to get it published. On the right-hand side is a tiny little early protopinniped brain case from the early Miocene of Oregon. And that was an experiment for me in acid preparation. Just put it, I actually acid prepped it out at my house. I put it in a little Tupperware container on top of the fridge. I take it out once a week, brush it for a few minutes, put it back in fresh acid, literally just 5% vinegar from the store, white vinegar, not balsamic. And it took, maybe 5 minutes of brushing a week, and finished it in about 2 months. So I like acid preparation because it appeals to my laziness, which is better termed efficiency. This is a skull of an extinct toothless walrus, and I'll talk more about this in a bit, called Valenictus. And this was in I think about a 80-pound block from Santa Cruz. And I spent about a year whittling it down to size with an air scribe. And then I had to go to New Zealand. So the last time you guys saw pictures of this, when I did this 10 years ago, it still had about 40 pounds of rock attached to it. I was even using this thing that was a literal handheld jackhammer with about a 1/2 inch wide bit that would, fire 2 by 2 inch chunks of rock 30 feet across the prep lab. And we were worried about breaking windows. That was a very fun tool. We don't have one of those here at College of Charleston. So instead, once it got here in 2017, I took it out back, and literally just hammered it with a chisel, broke off about 10 pounds or so, and then started acid preparation. So here we are. This is the specimen on the upper left. I was nervous about acid preparation, so I started it about 6 months after the fossil got here. But the top middle shows what it was like about halfway through the acid prep. By volume, about 2/3 of the way through time-wise, because once you get a smaller volume, the surface area increases relative to volume and the reaction speeds up. So this last bit is just about 4 months worth of acid preparation. And those scrape marks are from the little handheld jackhammer, the air scribe. All right, so that brings us to the Parissima Formation itself. It's broadly exposed near Moss Beach. Actually, if you go to the Fitzgerald Marine Preserve at Seal Cove, you're looking at marine invertebrates in between layers of the Parissima Formation. So it's exposed there. It's exposed up at Point Reyes along Drake's Beach and Drake's Estero. It's exposed pretty much along the entire coastline of Half Moon Bay from the Half Moon Bay Ritz-Carlton all the way down to Pescadero, which is where this photo is taken from along that section. It can be anywhere from 300 meters to 1.7 kilometers thick. It's mostly sandstone and siltstone with some shaly units representing deposition on a continental shelf between 10 and a little over 100 meters deep. And then it's got a lot of fossil mollusks, crustaceans, and fossil vertebrates. And one thing you can't see, but I can see, are rows of nodules that are just chock full of scallops that are about the size of a small plate. Capitola has some pretty famous shell beds. So here is my darling wife, who's not very tall. So these shell beds are actually not that thick. These are deposited at about 15 meters water depth based upon the rock type and the bedding patterns we see. But those are basically shell gravels. Some of these are storm deposits. Others are literally the troughs between sand dunes on the seafloor filled with shells. So if you go to Capitola and other spots and you look for marine invertebrates, you'll find occasionally echinoderms like this extinct ancestor of the modern Dendroaster eccentricus. It's a little more squat from side to side. Things like gooey ducks. This is one of the larger mollusks at this site. You'll often find little fragments, but occasionally, if you're very lucky, you'll find whole crabs or parts of crabs. So this is an extinct species of cancer crab called Cancer davidi that was originally named from the Kettleman Hills in rocks of the same age deposited in the San Joaquin Valley when it used to be a little marine embayment. One of my more recent finds was this, which I originally thought was a sheep or decorator crab in the genus Loxorhynchus. These specimens are going to be under study soon, and the crab expert tells me that these are actually not sheep crab carapaces. They're actually Macrocheira, which is the same genus as the modern Japanese spider crab, the one that's like 10 feet across. When you go out and looking for fossil vertebrates, you're looking for bone and teeth. Often they're pretty nondescript. So you guys can unmute your mics for a sec. Who thinks they know what this bone is? Class quiz. I'm a professor, so I do this all the time. Who can identify this bone? You're being a paleontologist for a minute.
Turtle.
Well, it is a marine mammal fossil. But that's an important point. It could be, you don't know that. I know exactly what it is because I dug it up. And I also knew what it was when I saw it. But what do you guys think?
Seal? Sea lion? Pinniped?
What part?
Ooh, flipper. One of the appendages.
Vertebrae.
What part of the flipper?
Oh.
Is it a humerus? Is it a scapula? Something else? It's not enormous. Well, maybe it is, depending upon the part.
I'm so bad with animal anatomy, so yeah, I have no clue.
Any other takers? All right, so this highlights something really important, and that is you need to have a search image. You need to know what to look for, but you also need to be familiar with anatomy. And so my brain is sort of a skeletal atlas of every marine mammal skeleton I've seen, modern and extinct. This is a phalanx of a baleen whale. It's about 4 inches long. It's quite heavy. It's got a lot of gypsum encrusting it and a little bit of a sandstone nodule stuck onto it. I was actually cleaning it off today. So you also have to identify fossils based upon what you see. You can't dig up every fossil carefully because you don't have enough time. And so it's actually, I find a lot easier. There's different strategies, right? You can be picky and say, oh, I don't think that's important and I'm on too much of a time crunch, so I'm going to leave it. Versus, I really know what this is. The other problem is the more that's exposed, often the more damaged it is. So there's always a trade-off. Something that's really damaged, you got a nice cross section through it where half of it broke off. Yeah, you can figure out what it is, but half of it's gone. So when something's just poking out like this, that's my favorite when you find it, because I'm reasonably certain what it is. But what I do know for certain, even if I'm wrong about that, is that it's going to be complete. And this is indeed a beautiful finger bone. All right, now there's a lot of different species from the Boessenecker Formation. We got sharks and rays, including threshers, the giant shark megalodon, early great white sharks, basking sharks, a bunch of different rays, makos. We even have Pristiophorus, which is a saw shark, which is now extinct in the eastern North Pacific. There are giant sturgeons, probably like 15-foot long sturgeons. An extinct species of sturgeon, by the way, wolf eels, Epinephalus. I can't remember if that's, oh no, we got Epinephalus is sister species to the Goliath grouper, I think. And I think there's actually Stereolepis as well, which is the giant sea bass. Oncorhynchus rastrosus, which is the giant extinct saber-toothed salmon, tuna, so on and so forth. Birds, we got all sorts of birds. Most of them are either gannets, which are now completely extinct. We've also got a ton of different types of early auks and puffins, including the flightless penguin-like Mancalline auks like Mancala and Myomancala. There's a bunch of fur seals, no sea lions, surprisingly, and a ton of walruses. 1, 2, 3, 4, 5, 6 species of walruses. And I'll talk at length about the different cetaceans. And of course, we've got an extinct sea cow, the ancestor of the stellar sea cow, and one sea turtle, an early leatherback. Most of these 89 marine vertebrate taxa are not published. So everything in red are unpublished. Everything in white has been published. So there's a lot of work to do. I'm slowly changing this to more and more and more white, but there's a lot of legwork. Out of these, about 12 or so are likely new genera or species. Some of these are highlighted. There are a lot of marine vertebrates that are not marine mammals. I'm not going to talk very long about them, but here's some examples, some of the more common or noteworthy ones. On the upper left, we've got a beautiful tooth of a great white shark found by my wife a few years ago. On the right-hand side, from the same locality in Half Moon Bay, is the humerus, and just half of it, of Pelagornis, which is a giant bony-toothed bird. This individual specimen is a minimum of 2.5 million years, which is the youngest well-dated specimen of one of these ever discovered anywhere on Earth. There are probably younger specimens waiting to be discovered and published, but this is it so far. The humerus itself would have been almost 3 feet long. So this is a bird with about a 20-foot wingspan. On the left is the geochronologically youngest fossil of a leatherback, which normally you find them in tropical deposits. And that I pulled out of the cliff in Santa Cruz, and my undergraduate student Bailey published that about a year and a half ago. It's got a thicker shell than a modern leatherback, which sets it apart. All right, I deleted my slides on fur seals. So sorry about that, but we will talk about walruses here for a minute. Walruses walruses had a center of origin in temperate latitudes in the North Pacific. And most of the very early fossil walruses we have are about 16 to 17 million years old. And we find them in places like Newport, Oregon, and Orange County. Most fossil pinnipeds you find that are younger than 15 million years old are walrus fossils. Maybe 1 in 10 will be a fur seal. So we've got Boessenecker Santa Cruzensis, named after Santa Cruz, that was found right near the lighthouse. On the upper right-hand corner, we've got Gomphataria. That's a new species we're currently working on describing. Would have looked like a gigantic California sea lion with a huge sagittal crest, but it had short, stubby tusks that pointed out straight. It had lower tusks as well that also pointed out straight. In the middle, we've got a bunch of isolated teeth like this one of Oso tabenis, named after the Oso sand in in Orange County. And that's a gigantic sea lion-like walrus. And then on the left-hand side is Valonectus, which is my personal favorite. I'm working on describing this skull right now. This is found by, at the time, 13-year-old Forrest Shepard, who's now, gone on to, I think he's already got his MD, caring sick people now. So he's grown up a little bit since he found this, and that's how long it took to clean the specimen off. So if we look at it, it's about 40 centimeters long. It's pretty hefty. It's about the same size as a modern walrus skull. It's a lot more elongate, so it's a little bit more in proportions like a sea lion. However, how many tooth sockets do you see? There's only 2, 1 for each tusk. There are no tooth sockets behind the canines. This is a toothless walrus. There's also no tooth sockets between the canines. So this lineage has lost all of its incisors, premolars, and molars. It has no lower teeth at all. And we know that based on more complete fossils from San Diego. Modern walruses don't chew their food. They suck the meat right out of the shell, and the shell doesn't even enter the oral cavity. based upon what we know of modern walruses, we think Valanictus just ditched the teeth altogether for more efficient suction, and probably just murdered a ton of clams. All right, now this is the American Cetacean Society, so we're finally on to cetaceans. There's a lot of odontocetes or toothed whales from the Parissima. We have a couple of monodontids, which are beluga and narwhal ancestors. So we got Denebula, which is a unique temperate to warm temperate species of beluga, originally reported or described from rocks of the same age on Isla Cedros in Baja. And there's maybe a couple of different species of belugas from the Parissima. That skull on the upper left still has a big concretion stuck to it, so I need to get it on loan from Berkeley and just drop that sucker in a vat of acid and get rid of that rock. On the right-hand side, we've got a globocephaline. That's an extinct pilot whale. That fossil has sort of a combination of features of false killer whales and pilot whales. In the middle, we've got a delphinid-like early porpoise. Modern porpoises have symmetrical skulls. Delphinids have asymmetrical skulls. And so this is in the process of losing that asymmetry, but still having a bunch of delphinid-like features. On the lower left is Albirio, which is a bizarre extinct family closely related to belugas and porpoises. And then on the right, we'll talk about Parapontoporia here in a moment. Parapontoporia is this extremely long-snouted dolphin. It has more teeth. I think the highest tooth count of any mammal ever to exist. 90 teeth per quadrant, so that's a total of 360 teeth all at the same time. We've got a complete skull from San Diego, and then on top there, that's a specimen from Opal Cliffs in Santa Cruz. And that skull is on display at the Santa Cruz Museum of Natural History. There's a life restoration that's my own artwork of a pod of Parapontoporia. And on the bottom left is the baiji. That's the recently extinct Chinese river dolphin, Lepodes vexillifer. Lepodes is the closest extant relative of Parapontoporia. Interestingly enough, Lepodes is a river dolphin. Parapontoporia is mostly found in marine deposits, but the youngest known specimen of Parapontoporia is an earbone from lake deposits in the Central Valley right after the San Joaquin Seaway closed up. So Parapontoporia may have independently also evolved towards riverine habits, just like the baiji. Unlike the modern fauna, where most of the medium to small size odontocetes are all delphinids, delphinids are quite rare in the Parissima Formation, and the group that seems to have taken that spot before delphinids radiated were the porpoises. We've got that asymmetrically skulled porpoise there in the lower right, which I think might be the same genus as Haborophacina from Japan. Rock, same age, probably lived across the entire North Pacific. At the same time, we have ear bones that look like Pneumatophacina, also from Japan. We'll talk about this goofy thing, semirostrum, which has this bizarre jawbone that sticks out beyond the rostrum here in a moment. On the lower left is the earliest fossil record of the genus Phocina, which is what includes the vaquita and harbor porpoises, along with burmeisters and spectacled porpoises. Those are all in the genus Phocina. That skull is from Half Moon Bay, and it's about 4 to 3 million years in age. So we got a bunch of different porpoises all swimming around at the same time, including this thing, Semirostrum cerutii. Semirostrum was found, that skull on the right-hand side, that the upper jaw is complete. It's got this bizarre toothless paddle-like extension of the lower jaw that jutted out way beyond. That's the original specimen of Semirostrum found in the San Diego Formation, which is the same age as the Parissima and shares a lot of marine invertebrates. On the left, is it's actually a composite. It's two different specimens. One, the jawbone is about 3 million years old, and the skull is about 5 million years old. But that's the same species, Semirostrum cerrutii. We think Semirostrum used its paddle-like chin to disturb sediment on the seafloor and maybe push through it like a plow and catch whatever little critters were burrowing in there, maybe like worms, sea cucumbers, etc. And it's got this really unique wear facet on the side of its teeth that suggests sand is running right down that line between the upper and lower lips. So a little bit of sand just getting right on the side there. And I added in this illustration a skull of Valimictus, that toothless walrus there poking out of the sand. As I mentioned already, we have a pilot whale-like species known from this very beaten but enormous skull. And these ear bones, we're not sure if they represent the same globicephaline or not. They might. However, based upon the size of the ear bones, the A, B, and C, that's a modern pilot whale for comparison. We think it's actually probably two different species. Neither of these are a perfect match for either Globicephala or Pseudorca. So we weren't able to assign it to a modern genus. In 2007, we're done with toothed whales now, talking about baleen whales. I found my second baleen whale skull. This is Herpetocetus, which is a dwarf baleen whale. This is an adult, so I don't have any scale here, but the partial skull is about 1 meter long. There's a question coming in from the chat. The size of the pilot whale, that individual whale probably would have been about 18 feet, I think, somewhere plus or minus 1 foot, a little bit smaller than a full-grown modern pilot whale, which I think are just a hair over 20 feet, if memory serves, or even bigger than that, I think. Don't quote me on that. I studied the dead ones. This is in soft rock. This is a kind of around opal cliffs. This section of cliffs is now covered up by concrete. So I'm glad I got this out when I did. It took a couple of days to get out. The block I'm working on is the larger piece that you see there on the right. And I'm very scrawny. That's because this is 2007, so I was about 22 here. Herpetocetus itself was only about 4 to 5 meters long. It's quite primitive as far as baleen whales go. It's also known from Belgium, the East Coast here. I found Herpetocetus here in South Carolina, and also Japan. It never made it to the Southern Hemisphere for some strange reason, but was obviously swimming through the Arctic during the Pliocene epoch. It also has this bizarre jaw joint that, let's see if it comes up. Nope. It has this bizarre jaw joint that prevented it from opening more than about 30 degrees. So we think Herpetocetus was a suction feeding specialist, a lot like a modern gray whale, only gray whales can lunge feed for fish or plankton like a humpback or fin whale can. They just usually don't. Herpetocetus, on the other hand, was basically locked into suction feeding. And when we lost all of this shelf space, all this feeding habitat at the end of the Pliocene, which we'll talk about here in a bit, it basically didn't have enough food to sustain it. We get a large number of rorqual fossils, so Balanopterids, ancestors of minke, fin, humpbacks, etc. Balanoptera cortici porticii. This is a species originally described from Italy that we also get here in the North Pacific. For some reason, we don't get it in the Western North Atlantic here on the East Coast. So we have no idea how it crops up in California and the Mediterranean without showing up in the Atlantic. The one on the lower left is a humpback whale like tympanic bulla. This is one of the ear bones. And then on the right, we've got two skulls both from Opal Cliffs in Santa Cruz, of Paraballenoptera, which was named that because it looks a lot like Ballenoptera, but it is clearly something that evolved in parallel. Paraballenoptera itself, here on the lower right, was found at Bolinas and excavated over a 10-year period, literally as chunks of the concretion were falling out of the cliffs at Duxbury Reef near Bolinas and Marin. This is from the Santa Cruz Mudstone, so the unit below the Purissima Formation. Staff at College of Marin collected these blocks. And sometimes they go out there every day during the winter to make sure they were there when the blocks fell off in case the waves carried the blocks with the bones away. And there are some missing pieces, but they got most of it. And it's at California Academy of Sciences now. This display is at the Drake's Beach Nature Center at Point Reyes. The new skull is a lot better preserved. That was found during construction of that seawall I mentioned. And that's a UC Berkeley specimen. One of my favorite baleen whales I discovered in winter 2004, and I came back with a permit in hand and started digging it up in August 2005 while I was still 19. So this is a photograph of the excavation site near Pomponio State Beach in Half Moon Bay. I had a permit for this locality. And here we are digging perfect height. It's only about 2 feet above the beach. There's scrawny me with a partial plaster jacket. And after we've hacked this 6-foot wide hole in the cliff, it goes in about 3 feet. And then that's my wife and I visiting the site 5 years ago, so 10 years later. I've filled out a little bit. What hasn't filled out is the sand dune. That sand dune has now been eroded away, and there were times when this hole was about 20 feet above the beach. So I excavated this about 6 months before a winter storm eroded away the sand dune that you'd walk up to get to this fossil. And had I waited a year, I would have had to wait until basically another decade until the sand dune built back up again. That specimen I spent about 5 years preparing at Museum of the Rockies. I took this 200-pound jacket in the back of my tiny Honda, drove all the way across the western US back to Montana State University, and started slowly preparing this thing out. Eventually, I realized it was a new species, probably in the genus Ballenoptera. It's very similar to a modern minke whale. So I named it Ballenoptera bertae after marine mammal paleontologist and colleague and friend of mine, Annalisa Berta at San Diego State University. And it's roughly about 2.5 to 3.3 million years in age. It's quite small. The whole skull is only about 1 meter wide. So it's about 3/4 the size of a modern minke whale. That's what the whole skull would look like when complete, very similar to a minke. And so I reconstructed it a lot like a modern minke whale. You put it all together and we've got this fossil assemblage of marine vertebrates that looks quite a bit different from today. We got a lot of porpoises. We have a lot of extinct species and genera of baleen whales that look really similar to modern relatives, but none of them are immediately ancestral, which poses a problem because these fossils are only 3 to 4 million years old. We know that the earliest fossils of a lot of these modern genera and species show up in the Pleistocene, and extinct species of things like humpbacks and minke whales and others show up in the North Atlantic 4 to 5 million years ago, but they're not here. As a matter of fact, most of these go extinct sometime within 1 million years after the deposition of the Purissima Formation. Everything without an X on it is a survivor. Christiophorus, that saw shark, they still live, but in the tropics, very far from California. So I put an X on that one, for example. Others are completely extinct, like Herpetocetus and that skimmer porpoise, the tropical, or sorry, temperate walruses, and that bony tooth bird, along with gannets. Well, gannets are not completely extinct, but they're extirpated from the North Pacific. So what happened to this fauna? And more importantly, what happened with the modern fauna? When did the modern fauna show up? So if you start tabulating the ages of a lot of these fossil occurrences, you see a couple patterns. Most of the species present in the Persimmon Formation disappear at the end of the Pliocene. A lot of them are also unique to the North Pacific. So we've got this, a lot of endemic species that are very different from what you see in rocks of the same age here on the East Coast, Europe, New Zealand, Australia, South Africa, etc. Most marine mammals from the Pleistocene, as I've mentioned, belong to extant genera or species. And so we have this Pliocene period of faunal endemism. There's got to be some sort of extinction event or rapid period of faunal turnover around the Pliocene-Pleistocene boundary, during which this 2 million year period, which I kind of often call a black box in marine mammal evolution, we have the loss of all of these extinct genera and the loss of the Pliocene fauna and the origin of most of our modern species. It's kind of tempting to, draw a big bold line there at the Plio-Pleistocene boundary and say, oh, well, that's where those fossil records end. So that's where the extinction is. The problem is that the early Pleistocene marine record is really terrible. So that might be an example of quote unquote what we call pseudo extinction. A lot of species appear to go extinct because the rock record ends there and we've got a big gap in time where there's no sampling. And if you look, a lot of these Pleistocene occurrences like Eumetopias, Xylophus, a lot of these pinnipeds don't show up until the middle Pleistocene. That's because the middle Pleistocene is where we start getting even a patchy record. Some are survivors. So Herpetocetus is an extinct genus that survives for a while into the Pleistocene. And we think when it goes extinct, that's right about when we get the really high amplitude changes in sea level that would erase all of the shallow shelf environment that they would need in order to sustain a viable population by suction feeding or benthic feeding on the seafloor, like a gray whale. We think during these times of small continental shelf, gray whales were able to revert to humpback-like filter feeding instead of benthic feeding. Herpetocetus was screwed, on the other hand, and goes extinct around 700,000 years ago. This all used to be speculation and a lot of arm waving, but my colleagues a few years ago looked at some broader patterns and found that sure enough, during the Pliocene, because of the loss of all these different lineages, there's a very elevated extinction rate for marine mammals and also other marine vertebrates, so sharks, sea turtles, and seabirds. Most of the critters that go extinct between the Pliocene and the Pleistocene are coastal rather than pelagic species. And of course, they tied this in, and I think rightly so, with this change in sea level from the Pliocene to the Pleistocene. So what happens in the Pleistocene, you get big ice caps. When ice caps grow, sea level falls. All that water's got to come from somewhere. Most of it comes from salt water. So we've got this is not sea level itself, but actually the amount of continental shelf space that's under about 50 meters water depth or so. And you can see there's drastically less continental shelf during the Pleistocene than there is during the Pliocene. That same thing at the same time is also why the Pleistocene marine mammal fossil record is so terrible, because sea level is so low. Most of the Pleistocene fossils are like 50 miles offshore. We get lucky in a few places though. One of those places, unfortunately, is not Santa Cruz or Monterey, But up in Humboldt County, we had the Eel River Basin, which was one of the only places from about 2 million to 1 million years ago that was dropping down so rapidly that it was actually below sea level. These rock units, the Thaler Formation and Rio Del Formation, they're each many, many kilometers thick because the basin was subsiding so rapidly. It filled up with mud really quickly. So fossils are very rare, unlike Santa Cruz, where I can go out to Santa Cruz and say, I'm only going to collect skull bones today or teeth. Up in Humboldt County, you got to collect everything because you're lucky if you find a single bone. They're spread few and far between because that sedimentation is so much more rapid. We get some of the only early Pleistocene marine mammals from the entire Pacific Basin here in Humboldt County. These are usually in spots like some coastal cliffs, but also just like poison oak infested creek beds. I don't go in there. I let my buddy Ron Bushel, who collected most of these, he's immune to poison oak, so he collected most of these. All of these are, well, the top two are the earliest records of gray whales and fin whales in the Pacific Basin. So gray whales have only been here for less than 2 million years, which is pretty neat. We've got, just last year, my PhD friend, lab mate, Chengshu Sai, published a mandible that's about 3 million years old from Belgium. So gray whales show up earlier in the Atlantic than they do in the Pacific. And of course, they were hunted to extinction in the North Atlantic by about 1600 or so. And they show up in the Eastern North Pacific about 1.8 million and about 2.5 million in Japan. So North Atlantic, Western North Pacific, and then California is the last place they show up in the fossil record. Fin whales show up around the same time, or slightly younger, I should say. That's a big, beautiful ear bone my buddy Chris found. Other fossils from Humboldt County are survivors. So Calorhinus, we've got this beautiful jawbone. This is a primitive version of a modern northern fur seal. It's still got some double-rooted teeth instead of single-rooted. That jawbone is from Scotia Bluffs. It dates to about 1 to 2 million years in age. We've got Calorhinus from the Pliocene, like the Purissima Formation. We got modern Calorhinus, so it's sort of a continuous record of this genus. It's the only pinniped that has survived every extinction event in the Eastern North Pacific over the last 5 million years. Because of that, not only does it get a gold star, but it also is my favorite pinniped in the North Pacific today. Even though it's not quite as charismatic as a walrus, it tells a really interesting evolutionary story. And then, of course, we have fossils of stellar sea cows. There's a skull cap from the last interglacial period from the bottom of Monterey Bay. So we know they were here during the Ice Age, but they actually evolved here on the California coast before they made it to Arctic waters. So we've got Pliocene. We've got actually the Pliocene species, Hydrodamnus questae, was 30 feet long, a little bit bigger than the modern species. That vertebra is probably the giant extinct Pliocene species that survived a little bit into the Pleistocene before shrinking down and turning into the cold-adapted species that Georg Wilhelm Steller found on the Bering expedition in the 1730s. And then, of course, one of Monterey's most famous marine mammals, I can't leave sea otters out of this. Sea otters are real newcomers. This bone, also found by my buddy Chris, he's the one who's looking over that 40-foot tall cliff on Steamer's Lane. He found this in the Merced Formation, which is kind of related to the Purissima, and based on beautiful strontium isotope dates from fossil plankton from this locality near Daly City, we're able to tie it down to basically like a 50,000 year interval. So it's somewhere between 670,000 and 620,000 years old. That's the oldest confirmed sea otter from the Pacific. There are older fossils from Alaska and from England. So sea otters actually have a European origin. And this has been a point of debate amongst paleontologists, but the sea otter fossils are so crappy that we can't reconstruct their relationships based upon the anatomy. We have to go based upon identifications and ages, which is kind of like how paleoanthropology has been with hominid skull fragments for the past 50 years. So when I published this, I did a bunch of cleanup on the otter fossil record and proposed a trans-Arctic dispersal into the Pacific within the last 600,000 years. So what explains this big difference between Pliocene and Pleistocene faunas? Well, there's a lot that's happened on the West Coast. Here's California during the Middle Miocene. Most of the Sacramento and San Joaquin valleys are underwater, and in some cases, hundreds of meters deep, a very deep basin. The California Coast Range is a series of mountainous islands. By the late Miocene, some of these islands are moving north. There's still quite a bit of continental shelf depth ocean in that Central Valley, though. You actually see these provinces move north. This big chain of islands down near Santa Barbara, those are the transverse ranges and the modern Channel Islands. So the Channel Islands are kind of a good analogy for what these Coast Range mountains would have looked like. Most of the uplift of the Coast Range began during the Pliocene, which forms a barrier off to the west. What's also happening is the uplift of the Sierra Nevada, and we end up with this landscape during the Pleistocene and today during the Holocene epoch. So if we look at a comparison between the Pliocene in the last 50,000 years or so, there's one major thing that's missing from the California coast today, and that is really, really wide, very shallow embayments that must have just been packed full of clams, other marine invertebrates, highly productive habitats for things that with adaptations like a walrus or something like semirostrum, which is feeding on marine invertebrates from the seafloor, suction feeders like Herpetocetus, etc. One thing that hasn't been done is looking at the relative proportion of probable fish eaters versus benthic feeders in these faunas, but that's sort of a good good route for future research. So this is accomplished a few ways, and there's the approximate location of the Perisma. So it's connected to this inland sea called the Temblor Sea, which is basically the southern San Joaquin Valley. Those deposits that are inland basically form a lot of the badlands along I-5, right around Coalinga and Kettleman City. And the Kettleman Hills are a classic geological locality for studying oil traps. So we lose these shallow embayments, which is partly caused by sea level fall, but also by uplift. So we, I'm skipping ahead to number 3, we uplift the California coastline. It sort of forms a dam along the outer margin of that coastline. We also lose shallow embayments in the LA Basin. The LA Basin's super flat. Most of that was continental shelf as recently as 3 to 4 million years ago, as well as Orange County, San Diego, and much of Baja California for that matter. At the same time, it's also moving north. So it literally squeezes out this entrance, which at one point is called the Priest Strait. At the same time, the Sierra Nevada is being uplifted. Most uplift on the Sierra Nevada is in the last 5 million years. When you uplift mountains, erosion happens, especially when you make a mountain range high enough for glaciers. Glaciers scrape all that rock off, make nice new layers of sandstone and conglomerate, and that's got to go somewhere. Well, this nice marine basin gets filled in rapidly with many, many, many kilometers of sediment shed directly off the Sierras. So the eastern half of the Central Valley, everything basically east of I-99 is all just stuff dumped directly off the side of the Sierras. So it dries up, it gets dammed off and walled off by these two mountain ranges. We end up instead with this extremely rugged coastline that's famous for our kelp forests now. But maybe in the past, a lot more California was like, you know, Scammons Lagoon on steroids instead. All right, so to conclude, we had a very different marine vertebrate fauna right up until about 2 million years ago. The diversity in terms of the number of species and range of adaptations was similar to the modern fauna, but a very different composition. So instead of sea lions, we had walruses. We didn't have any true seals yet. No elephant seals, no harbor seals. They show up about 1 million years ago, just like sea lions did. Dwarf baleen whales, a diverse fauna of small odontocetes being formed by porpoises rather than delphinids. We still got some weird river dolphins with Asian affinities, temperate climate belugas. About 65% of the modern marine mammal fauna that we have here on the West Coast has evolved and appeared here in the Eastern North Pacific within the last 2 million years, likely driven by changes in circulation, global cooling, and I think changes in coastal geography as well. So with that, I'd like to open it up for any questions. How long might bone leftovers last from vertebrate whale falls in the deep sea, and how prevalent might extinct fossils or bones be on the present seafloor? That's an excellent question. There's a study based off of whale falls, actually in Monterey Bay, and they found that bone-eating worms in the genus Boessenecker could recycle a gray whale skeleton like an adult, 50-foot long skeleton. They could recycle the skeleton basically into little bone crumbs in under a decade. We have fossils here from the Oligocene epoch, about 30 million years old, that are literally just slivers of bone with traces from Boessenecker worms all over them. There is no evidence of bone-eating worms, however, in any bones in the Parissima Formation, likely because by the last 5 million years, Boessenecker stopped inhabiting continental shelf environments. We don't know why, and it's entirely unpublished observations, but by the time you get to the Miocene, all bone-eating worm pockmarks on bone are pretty much just in deep sea deposits. And as for bones on the present modern day seafloor, they get fossils that are under a couple million years often get dredged up by fishermen. I've seen extinct beaked whale skulls dredged up off of Orange County before. Modern specimens, they get found on occasion by trawlers. They get found frequently in places that have a flatter coastline and a less destructive marine environment, like the East Coast here. Walrus skulls get dredged up off of New Jersey all the time, the Netherlands, Belgium, so on and so forth. Volunteers at digs. Unfortunately, I'm on the East Coast now. Sometimes we need volunteers. We usually try and pick from amateur collectors who know their way around a pick and chisel. For amateur fossil hunters, is it necessary to obtain permits? Yes. And so there are many fossil sites, including some of the ones I've talked about, where amateurs are not allowed to collect. So for example, one of those is the picture in the background here. That's the state park, and only scientists get permits to collect there. But if you want fossils that you can collect as an amateur, there are sites that are accessible, some in Scotts Valley maybe, but also Capitola. That's a great amateur-friendly site. Where did our two sea lions, Guadalupe fur seal, originate? Can you talk about their evolutionary origin? Xolophus and Eumetopius, the two sea lions on the West Coast, they don't show up in the West Coast fossil record until about 500,000 years, but they show up about 4 to 5 million years ago in Japan. They have a Western North Pacific center of origin. Guadalupe fur seal has no fossil record, and Arctocephalus in general doesn't have a good fossil record. We think the Guadalupe fur seal shows up, or we think that it immigrated based on molecular phylogeny. It immigrated from the southern hemisphere because it's closely related to the, oh God, what's it called? Juan Fernandez fur seal, I think, Arctocephalus philippii. It immigrated across the equator during the last glacial period, about 60,000 years ago. Private collections, this is a good question. I am all for private collections. I think scientifically significant specimens should be in museums. That is a whole Pandora's box of arguments. I think amateur collectors and private collections do a lot to advance paleontology. A lot of amateurs discovered some of the fossils I talked about today. Probably 3/4 of the fossils I showed pictures of were found and donated by amateurs. The juvenile T-Rex, not juvenile, sorry, the one that sold for a lot of money, Stan's an adult T-Rex that sold for like $30 million or some insane amount. That is going to have a ripple effect on paleontology for decades, and nobody right now is even aware of how extreme those changes will be. But for example, when Sue, the T-Rex of the Field Museum, when that was auctioned off in 1997 for $7 million, which sounded like a monumental sum then, let alone 30 million in the middle of a pandemic. That tripled the activity of commercial paleontology. Got a lot of people interested. A lot of people also like fossils purely as collectibles, curiosities, and as monetary objects, unfortunately. And so it also led to a lot of fossil poaching. So there's good private collecting, which is mostly what happens on the West Coast. And there's really, really bad private collecting where people sneak onto public or federal land, excavate fossils illegally, and then sell them. At Montana State University, actually at Museum of the Rockies, there's an Allosaurus skeleton that was illegally being dug by some Swiss commercial paleontologists off of, I think, Bureau of Land Management land, and the fossil's now known as Big Al. And so Museum of the Rockies got called in to finish the excavation after the Swiss paleontologists were caught and kicked out of the country. And that's how Museum of the Rockies ended up with the Wyoming specimen. I've caught some illegal diggers before, and usually they don't know about it. So I tell them, yeah, don't do it anymore. If you find something cool, call me and you can help me dig it out. But please stay to the localities that are legal for amateurs to collect at. So Point Reyes, most of Half Moon Bay, those are off limits. Most of Santa Cruz, however, is open season. And in Santa Cruz, I find because of the higher number of fossil collectors, I really have to hit the cliffs frequently in order to beat the amateur collectors to the good fossils. I also make friends with them and identify fossils, share literature with them. So I give them plenty of reasons to be generous and donate fossils to various museums. Any other questions?
So if there's no more questions, feel free to put it into the chat. I have a general question that I usually ask. What is your favorite thing as being a paleontologist, as well as do you have any advice to anyone who might want to become a paleontologist, amateur or, hopefully professional?
Oh God, there's a lot to like. Teaching is really fun. There's quite nothing like figuring something out for the first time, just as a science, but that's sort of scientific in general. But the biggest blast I ever get in my life is discovering something really cool on a cliff for the first time. And sometimes it's like, holy cow, what have I found? Oh my God, it's X, Y, or Z. Sometimes it's like, oh no, this is a really big whale and I don't think we can get it out of here safely. So sometimes I've seen skeletons that I've come across and be like, this is beautiful. It's incredible that I'm able to see this here at this moment, but I can't do anything about it. Moments of discovery are pretty great. Others are moments of enlightenment. On a day-to-day basis, they get to get really dirty. I have to clean rock fragments out of my hair every day when I'm prepping fossils. I get to train undergraduate students how to clean and study fossils, which is extremely rewarding, especially when they don't screw anything up or break anything. Yeah, playing with fossils every day is fantastic. And there's, you don't need a PhD to do it. Some of the smartest paleontologists I know are amateur paleontologists.
Awesome. And then any advice to any undergraduate or someone who wants to get into paleontology?
The best advice is don't worry too much about your chemistry and physics grades. Spend as much time doing extracurricular academic work as possible. Get started on an undergraduate research project if you can, because that, if you graduate with a 2.89 GPA, but you demonstrate that you're a qualified researcher, you'll get into grad school. Don't worry about the gen eds. If you get C's on them, you're going to be okay. Do well in the paleo and geology courses. Anybody who does paleontology basically needs to know not only their anatomy and a lot of evolutionary biology, but also geology. We kind of get doubled over by it because we have to know both topics, which is a little unfair, but keeps things interesting.
Awesome. I don't have any more questions to everyone. So if anyone has any questions, I'm going to feel free to just hang out for a little bit. But thank you so much for joining us. It was amazing talking, especially since a lot of us is in our backyard. And I hope you have a great night on the East Coast. Thank you so much for joining us.
Thanks a million for hosting this. I really appreciate the invitation.
Awesome. Thank you, everyone. Have a great night.
Take it easy, y'all.